In today's video, we're going to be looking at the reactions of aldehydes and ketones from the chapters 17 and 18, and in particular, we're starting by looking at the handout that has a summary of most of the reactions from the two chapters. The two-chapter reactions fall into a series of categories: strong nucleophiles, medium nucleophiles, and weak nucleophiles, and they give a variety of outcomes. What they have in common is that they all start with a carbonyl with no leaving group, so that would be an aldehyde or a ketone, or a nitrile. The nitrile reaction deserves a few special considerations. For example, in Chapter 17, we saw that nitriles will be having polar C and pi bonds, will add to the C, the delta plus C, if you have a strong enough nucleophile like a Grignard reagent or an alkylithium. The addition happens once, then you hang around to add dilute aqueous acid, and that dilute aqueous acid actually replaces the remaining nitrogen with a carbonyl. So this is a way to turn nitriles with this RC group into ketones, where it still has the RC, but it now has a new carbon-carbon bond between the R group from the alkylithium or the alkymagnesium and the carbonyl. Also in Chapter 17 was a reduction of nitriles, and reduction in the broadest sense means decrease in the number of C electronegative element bonds. In this case, the number of C triple bond N goes down to C single bond N. So we've reduced that number of bonds and or the increase in the number of CH bonds, and we in fact have increased the number of CH bonds here as well. This happens by lithium aluminum hydride adding a hydride H- nucleophile strong to the polar pi bond. The nitrogen then coordinates with the aluminum, a second hydrogen adds, and after hydrolysis the aluminum gets replaced with hydrogen, so we have now a completely reduced structure. Finally, in Chapter 18, we see hydrolysis of nitriles. Again, we have a polar pi bond. Here we have an acid, so we protonate first on one end, and then the water adds to the other end, and after a series of acid-base reactions and the NH3, or the nitrogen leaving as NH3, you end up with a carboxylic acid. In Chapter 17, we saw some simple addition reactions. We saw an equilibrium reaction in either acid or base of water directly to a carbonyl to make a hydrate. This is not a useful synthetic reaction, but it does occur. We also saw addition of irreversible nucleophiles like alkylithium or alkymagnesium bromide, which are known as Grignard reagents, directly to a carbonyl carbon delta plus to make the corresponding alcohol and a new carbon-carbon bond at the same time. We saw the addition of a strong reducing agent, increasing the number of CH bonds by the hydride adding to the polar carbonyl to make a alcohol that has an additional CH bond. That is reduction, loss of the polar CO bond, gain of the CH bond. And we saw Wittig reactions in our homework and in the last video, in which we take a strong nucleophile of a carbon next to a phosphorus reagent, a so-called Wittig reagent, carbon of the carbon, where this carbon nucleophile adds the delta positive carbonyl, makes a new bond, and after the phosphorus leaves in conjunction with the oxygen, we end up with a new CC pi bond in the place where the original CO pi bond used to be. Finally, in the ChemActivity, we saw the addition of sodium cyanide, a much weaker nucleophile, to a carbonyl reversibly in the presence of HCN. This reaction actually shows up in our textbook in Chapter 18. One additional reaction we saw in Chapter 17, and we will see again in Chapter 18, is that some nucleophiles, most specifically the strong-base nucleophiles alkylithium or magnesium, lithium aluminum hydride, sodium borohydride, and Wittig reagents add exclusively to the carbonyl carbon even when there's a conjugated alpha-beta pi bond. On the other hand, weaker nucleophiles, those that add reversibly, add predominantly to the beta position. They can also add to the 1,2 position, but that first reaction tends to be reversible, and we end up getting sucked down to this 1,4 addition product. And that's true for all the other nucleophiles we saw, including cyanide ion, alkylithium ion, a new reagent, dialkyl copper lithium, and we will see in the upcoming chapter that enolate ions also add in this 1,4 fashion. So what's left to talk about in Chapter 18? Well, primarily in Chapter 18, we're concerned with things that are very weak nucleophiles that require an acid to add and or create new carbon-carbon bonds. Okay, so they're all reversible reactions. In particular, we're going to be concentrating in the Monday Chem Activity 23B on the addition of primary and secondary amines, where that primary means that the nitrogen's attached to only one carbon, secondary to the nitrogen's attached to two carbons, and alcohols as weak nucleophiles. Since they're neutral, they require a strong mineral acid for addition, and they make new compounds, new functional groups, amines, enamines, and acetals. We will also look at aldol reactions. Aldol reactions are ones in which we have a carbonyl with an alpha hydrogen that can be removed by a base to make an enolate ion, and then the enolate ion becomes the active reagent for nucleophilic addition.